Welcome to my presentation on statistical models for predicting results in professional League of Legends. My name is Robbie Jadowski, and this project was also worked on by Stuart Cunningham. Statistical analysis of sports is an increasingly popular method for recruitment and strategizing in modern sporting competitions. With the rising prevalence of esports, in this researcher's case, League of Legends, this analysis can be applied to greater depth, as statistics and metrics can be gathered automatically by the game itself. The aim of this research is to build a statistical model using metrics from professional games of League of Legends to accurately rate team and player performance, with the intention of predicting the outcome of future games featuring those players and teams. League of Legends was released in October 2009, and in the years since its release, it has developed a competitive infrastructure across multiple regions that rivals that of traditional sports. Each region's competitive league features franchise teams that compete against each other in weekly broadcasts that regularly draw thousands of viewers and annual inter-regional championships that have drawn 44 million peak concurrent viewers during grand finals. League of Legends is a team-based strategy game where two competing teams of 5 players aim to destroy their opponent's base, canonically named the Nexus. Each game of League of Legends takes place on the same map, known as Summoner's Rift. Summoner's Rift is split into 3 lanes, commonly known as top, middle, and bottom. These lanes form a path that leads from one base to the other. The 2 sides of Summoner's Rift, referred to as blue side and red side, are separated by a river that runs from top lane to bottom lane. The area in between the lanes is known collectively as the jungle. The blue team's base and nexus is situated in the bottom left of the map, while red team's base and nexus is in the top right. Players select one of over 140 champions to control in order to complete the objective, and each possess abilities that aid in combat, navigating the environment, or supporting their team. Each player fulfills a different role for the team, much like the different positions in a football team. The roles featured in LoL are top laner, jungler, mid laner, bot laner, and support. Each corresponds to the area or lane of the map that the player will operate in during a game, with the support player often partnering the bot laner. These roles traditionally feature a typical character archetype, though there are exceptions and champions that buck the trend. For a team to reach and destroy the enemy's nexus, they must overcome a series of AI-controlled structures known as turrets. These structures are very difficult to destroy without assistance, which is usually provided by the wave of AI-controlled minions that spawn periodically from a team's base. These minions will follow a lane's path to the enemy base until they run into the opposing team's champions, minions, or turrets. Players must aid their minions in their advance in order to take down turrets and reach the opposing team's base, while defending their own turrets from the opponent. The map also features neutral objectives: Dragon, Rift Herald, and Baron Nashor. These neutral monsters can be defeated by a team to obtain permanent and temporary bonuses, ranging from additional movement speed, a percentage increase in ability power, or buffs to friendly minions to aid in sieging the opponent's base. Due to the asymmetrical nature of the map, granting the blue team easier access to the area that Baron Nashor spawns, combined with the pre-game champion draft where the blue side can choose their first champion before the red team, there is a debate that blue side has an inherent advantage compared to the red team, similar to the home advantage often seen in traditional sports. This advantage will be explored when analysing the data from competitive games, and considered when making predictions if such an advantage exists. This report is focused on 7 competitive leagues in League of Legends: the LEC from Europe, the LCS and LCS Academy from North America, the LCK from South Korea, the PCS from Southeast Asia, the CBLOL from Brazil, and the TCL from Turkey. While the Chinese League is the largest and perhaps most dominant region, there is insufficient data for each individual game available, so it is excluded from the analysis. By using the data from every competitive game played during the 2020 spring split from the 24th of January 2020 to the 2nd of March 2020, we aim to predict the outcome of games that take place in the 2020 summer split. Each training dataset was validated using 10-fold cross-validation. There was a total of 306 games in the 2020 summer split dataset used for testing. The data used in this report was obtained from an independent analyst, Tim Sevenhuisen, who runs the website oracleselixir.com. The training data featured 882 games of data. Each game includes 12 rows, 1 row for each player and 1 row for each team. In order to make the data usable, it was separated into 2 subsets, the raw data of per game averages of each team and the raw data of per game averages of each player. The team statistics include an opposite statistic for each metric. This is usually the opponent's statistic for that respective metric. Opposite stats are crucial for calculating the strength of schedule for each team and for estimating a team's defensive ability. Each statistic is a measure of each team's per game averages. The player statistics are measured using slightly different metrics. These metrics do not include opposite metrics and instead measure an individual player's per game average statistics. The players are separated by role, since different metrics can be more important to specific roles. For example, a support player will traditionally get less kills than most other roles, but will perform much higher in the ward placed and wards cleared per minute metric. Pythagorean expectation, or PE, is used to calculate the expected total wins for a competitor over a number of games. George William Bill James, known for his approach to analyzing professional baseball using data and statistics, developed the formula to predict a baseball team's win percentage from the observed number of runs scored and runs allowed during a given baseball season. In the original formula, W is the win percentage, S is the observed number of runs scored, and A is the observed number of runs allowed. James initially used an exponent of 2. Different exponents can be calculated for each team in order to more accurately predict win percentages, and methods to find those exponents, such as the Pythagorean formula, have been developed. Though originally used for baseball, the simple concept of an offensive and defensive stat forming the foundation of the PE formula means that it can be applied to other sports. The planned model for rating teams in League of Legends will be calculating an overall offensive and defensive rating for each team, so these ratings can also serve as the values used in the PE formula. Once the values of the PE formula for each team are known, we can use another formula to estimate the probability of one team beating another. James also devised log5, a formula that uses two teams' winning percentages to calculate head-to-head matchup probabilities. The log5 formula considers the winning percentage of Team A and Team B and returns the percentage chance that Team A beats Team B, from which we can easily calculate the chance that Team B beats Team A. We can experiment using this formula with the values obtained from PE and compare them to predictions from logistic regression models to see if it offers better or worse performance. If two teams have an equal record in sports, it can be challenged to determine which one could technically be considered the better team. One way of determining this is to assess the strength of schedule for each team. Assessing a team's strength of schedule, or SOS, can lead to interesting insights. Where a bad team who appears strong on paper may have only played against weaker teams, while a good team with worse statistics may have only played against stronger teams. This work will be taking SOS into account when analysing the dataset, since many teams in League of Legends do not play each other the same amount of times over the course of a split. Information about the mechanics of the formula used can be found in the paper. Using this formula, one can calculate what a team's adjusted stats would be for each metric and compare them to their actual performance. If a team's adjusted stats are lower than their actual performance, this would indicate that the level of their opponents was worse in that metric and vice versa. Before devising and evaluating a model, it is important to determine if the dataset is balanced or not. In this case, whether the side of the map a team starts on provides any advantage. While most physical sports feature a home advantage due to familiar locations, less travel time, or playing in front of their own fans, League of Legends takes place in a virtual environment. Therefore, no significant difference or advantage for either team should be discovered. Despite this, there are major differences between starting on either side of the map that could provide an advantage to either team. It may be argued that the blue side of the map holds an inherent advantage due to several factors. These include the asymmetrical geometry of Summoner's Rift and the isometric point of view favouring the blue side of the map. More importantly, the pick ban phase strategy of a team is often dictated by the side of the map the team is going to be playing. Data suggests that this side advantage does exist. In 2017, professional League of Legends games saw a period where blue side had a win rate of 64%, so much so that the developers of League of Legends have sought to balance this advantage through various balance updates, such as making dragons a more lucrative objective. The dataset used in this study includes 882 games, of which blue side won 477. This equates to a 54.08% win rate for blue side. A chi-squared test suggests that the side of the map does have an impact on a team's chance of winning. This infers that blue side are expected to be more prevalent in the dataset, causing a slight imbalance. Using all available metrics in a prediction model can be detrimental to the performance and prediction accuracy. Using a point biserial correlation coefficient, or PBCC, calculation for each metric identified which metrics strongly correlate with the result of a game. Two sets of calculations were carried out on each metric, one for the true stats of each game, and one for the per-game averages of each team in each game. The tables were split into calculations for blue side and red side, and ordered by the highest averages PBCC, converted to absolute value. The coefficient values can be used to calculate a weighting for each metric when producing a team rating. Another prediction model can also be formed by using these metrics as features, meaning that the results can be compared to the prediction models using all available metrics. Following Z-score normalization of the metrics, the next step was to determine the weight of each metric. Weighting was calculated using the PBCCs used earlier to select the most relevant features. After calculating the weights, an offensive and defensive rating performed using the sum of each normalized metric multiplied by its weight. This creates two new metrics, the offensive rating and the defensive rating. Figure 2 displays each team in terms of their offensive and defensive ratings, creating a visualization of where a team's strengths lie in their playstyle. These metrics can be considered opposites, lending themselves to being used in a Pythagorean expectation formula. To determine the most accurate PE exponent for the offensive and defensive ratings, we iteratively evaluated exponents between 0 and 10 and calculated the mean absolute error, MAE, from each team's predicted Y and actual X win percentages. This is done with the intention of finding the PE exponent value that minimizes the MAE. The values of the defensive rating were inverted and added to a constant of 5, since the formula relies on a lower positive value defensive stat being a reflection of a team's ability. We found a value of 1.82 was the most accurate single exponent used for this dataset, with an MAE of 0.0397. The MAE values for this exponent range are shown in Figure 3. Focusing on the performance of an entire team to predict results can be flawed for several reasons. In competitive LoL, teams may use substitute players to take the place of another player in a certain role. There is also the case of players transferring to a different team between each split. Teams will try to sign new players to replace underperforming ones, or more successful teams might attract the best players from lesser teams. Predicting future results only by a team's combined results could lead to problems if that team changes its roster. In this case, rating each player may result in more accurate predictions. By assigning each player their own rating, a modular overall team rating can be formed. Rather than choosing the same metrics for every player type in LoL, there is a reason to consider the difference in each player a player can assume, and what aspects of the game are important for that role. For selection of player metrics, the same process was followed as for team metrics, namely selecting the strongest correlation coefficients and weighting them accordingly. After selecting the metrics for each role, the next task was to arrive at an overall rating. The player statistics dataset is not suitable for an offensive and defensive metric split, so each player only has one overall rating based on the stated metrics. After calculating each player's rating, another model can be set up using the team's individual player ratings as a feature. Therefore, if a player is swapped out for a different one in a game, the rating will adjust to match the new player, affecting prediction outcome. A total of 7 sets of features and approaches were evaluated to identify the one resulting in the best prediction outcomes. The unadjusted per game metrics per team, the adjusted per game metrics per team, the 8 weighted metrics selected by their PBCC scores per team, the calculated offensive and defensive rating per team, a player rating for each player in both teams, actual win rate percentages of each team, and expected win percentage calculated using the Pythagorean expectation formula for both teams. Approaches 1 to 5 made use of the logistic regression to predict game outcomes, while 6 to 7 made use of the log5 formula for prediction. The following metrics were used to measure performance of the approaches: classification accuracy, F1 score, area under curve, Matthews correlation coefficient, and log loss. Following training of the logistic regression models and the calculation of the log5 outcomes, the results were obtained for each approach using the test data set from the 2020 summer split, as shown in Table 6, where the highest performing outcome for each metric is highlighted in bold. The player rating model scores the best in each performance metric, especially MCC, while all models suffered lower F1 scores for predicting red wins than predicting blue wins. Prediction performance of wins for the player rating model is illustrated in Figure 4 here. The player rating approach achieved a significant classification accuracy of 67.3% when predicting 306 games from the 2020 summer split, which is significantly better than chance. As this result is a first iteration, it stands to reason that improvements are possible. The findings may also have utility in player scouting, where a player may be performing better than their competitors but is on a worse performing team. The win rate approach scored the worst in all metrics other than log loss. This confirms assumptions that can't be made based on previous results of teams alone, but further investigation into their actual performance in other game metrics reveals that they will better influence future results. Since the approaches used per game averages rather than game by game data, they were unlikely to achieve a 90% classification accuracy due to the inevitability of upsets. Future work should include a way to update a model after each game is played and weight more recent games higher than older games when calculating a team's strength, eventually forgetting those games as they become irrelevant. For additional experimentation, a combination of team ratings and player ratings would likely be ideal. Due to the small team size in League of Legends, a roster change can have massive implications on the future performance of a team. There is also precedent for dominant teams falling even without roster changes. This concludes my presentation on statistical models for predicting results in professional League of Legends. Further details and elaboration can be found within the full paper, alongside the relevant references that made this research possible. Thank you for listening.